This is John Whitaker for the Mathematical Analysis 1 class, and this is our 27th video lecture. And today we want to continue our work on continuity and some connections between continuity and some topological properties. So I'd like to start today with a theorem. It says, suppose x, y, and z are metric spaces E is a subset of X. F maps E into Y. G maps Y. Well, G maps the range of F, that's F of E, into Z, and we're going to define H is the mapping of E into Z defined by H of X is equal to G evaluated at F of X. That's the composition for every X in E. Let me make these little X's. I'm going to get confused with the big metric space X. What we just had was the definition of a composition of functions. Okay. Now, what we want to talk about is some qualities for F and G and what quality it gives the composition, namely continuity. Okay. So if, still part of this theorem, if F is continuous, at a point P in E, and G is continuous at the point F of P, then H is continuous at the point P. Okay, so this is saying that the composition of two continuous functions is going to be continuous. And here's the proof. We're going to do this by the definition of continuity. So we want to show that H is continuous at P. And I'm not writing down all the hypotheses here again. We're just going to assume the conditions of the theorem without writing them down. And so how do I show that H is continuous at P that's an element of E? Well, what we do from the definition is we'll have something greater than 0 be given. And what we need is a delta bigger than 0, such that for all x NE with so for all x in E with the distance, or the metric on x, between this little x here, and that's what I should have written up there, little x, and P being less than delta, then h of x, the distance in Z between h of x and h of P will be less than epsilon. That's what we want to do. We want to find that delta. Okay. Well, we'll start off by noting that since G is continuous, on or at f of P, there exists a delta sub 1 greater than 0, such that for all, I'll call them y's, there's an element of f of D, so that's the domain of G, f of D, such that the distance between y and f of P is less than delta sub 1, then the distance in Z between G of y and G of f of P, G of f of P is h of P, that's going to be less than epsilon. Well, we can now turn to F and say, well, since F is continuous to P, there exists a delta, that's the delta I need, that's greater than 0. Now, what is being said by the previous line? Previous line says, hey, look, when you look about f of E, when you look at f of E, as long as the points in f of E are close enough within delta sub 1 units, G will, as long as the points y are within delta sub 1 units of f of P, the G will grab those points and send them with an epsilon of G of f of P. Okay? And so G is going to grab things that are close to f of P and send them things that are close to G of f of P, as long as you're within, the input values are within delta 1 units. What I want to make sure is that the f values that are sent to these such y's, they're going to be within delta sub 1. The output values for f need to be within delta sub 1 of f sub P. But I can make that happen because f is continuous at P. And what I'm thinking of is for the continuity of f with this definition, this delta sub 1 is acting like an epsilon. And so there's a delta for this epsilon, if you will, that I'm calling delta sub 1, since f is continuous at P, such that for all x element of E with the distance in x of x to P being less than delta, then that's going to force, by the continuity, that the distance in y between f of x and f of P to be less than delta sub 1. Okay? That's what we have. Okay, so here, what we have then, thus for all x between x and p being less than delta. Let's write that down. This would imply that the distance in y between f of x and f of p will be less than delta sub 1. But those are input values for g, so that implies that the distance in z between g of f of x and g of f of p, that will be less than epsilon, that's delta sub 1 there. So, writing this in terms of h, for all x in e with the distance in x between x and p being less than this particular delta, we have this conclusion, which is written in terms of h, it would say the distance in z between h of x, that's what h of x is, and h of p, because that's what h of p is, that will be less than epsilon. And that tells us h is continuous at p. And that's the conclusion of this proof. Okay, we've been talking about continuity at a point, but we can talk about continuity on a set, and we're going to do that next. But first we need a definition of how we're going to talk about that. So we're going to let x and y be metric spaces. Let E be a subset of X. Suppose F maps E into Y. Then we say F, so here's what we're defining, is continuous on E if F is continuous for each P in E. Okay, so that's its definition. And what I'd like to do next is write up a fact about continuity, a function that's continuous on domain, if you will, E. So here's the theorem. It says a mapping F of a metric space X into a metric space y is continuous so here when we talk about it's continuous, we mean on x. Okay. If and only if the pre-image of V is open in X, for every open set V in Y. So what this says is that if you take the inverse image of an open set from Y, it's going to be open in X. And that's what's sufficient and necessary for F going from X to Y to be continuous on X. Okay, so let's look at the proof. Let's let F map X into Y. It's an if and only if proof, so we start off with this direction. And here, we suppose F is continuous on X, and our goal is to show that the pre-image or the inverse image of an open set from V is open in X. So we're going to, and let V be open in Y. So we want to show its inverse image is open in X. Let's write that down. We want to show that the inverse image of V is open in X. Okay. So how do we do this? We've got to show that if you give me some point in this inverse image that is an interior point. Okay? So let P be an element of this inverse image of V. We want to show, we need to show P is an interior point of F inverse of V. Well, what do we know? We know a couple things. First of all, we know what F inverse of V is. So since F inverse of V, it consists of, if you will, I'll say all the little a's that are element of the space X, such that F of A is an element of V. That's what it is, by definition. Then, since P is in the inverse image of V, then F of P is an element of V. And since F of P is an element of V, and V is open, then there exists an epsilon greater than 0, that's the radius of the neighborhood, such that the neighborhood centered at F of P, radius epsilon, this is going to be contained in V. What I'm saying is that F of P is in V. V is open, so everything in V is an interior point of V.
And so if f of p is an interior point, there exists some neighborhood of f of p that's totally contained in V. Okay. Well, what is this neighborhood? That is the collection of all y's, element of y, such that the distance in y between the y's and f of p will be less than epsilon. That's what that neighborhood is. That's contained in V. All right. Now, what do we also know? We're assuming that f is continuous. Since f is continuous, it's continuous on x. But if it's continuous on x, it's continuous at every point of x, so it's continuous at p. Then there exists a delta bigger than 0, such that for all little x element of big X with the distance between x and p being less than delta, then the distance in y between f of x and f of p will be less than epsilon. So now consider an x sub 1 as an element of the neighborhood centered at p of radius delta. Okay. Then, well, what does it mean to be, for x sub 1 to be in this delta neighborhood of p? Then the distance between x sub 1 and p is going to be less than delta, which implies so first of all, if it's less than delta here, that implies I'll say therefore this neighborhood centered at delta of p will be contained in V. Now that doesn't make sense. Wait just a second, I need to think about this. No, not in V, but rather in the pre-image of V. Right, so what are we saying? What we're saying is that I've made a little bit of an error here in terms of explaining this. Let me back up. Okay, so X is in this delta neighborhood. Okay, what does that mean? That means, well, I think maybe what I said was okay. So that means that the distance in y, yeah, so let's back up. So the distance between in x, between x sub 1 and p is less than delta, which implies, I'm sorry, that the distance, because of the continuity, between f of x and f of p is less than delta. So that means, And so here this should be x sub 1. So what that means, now I'm on the right train of thought, it's less than epsilon. That's what this should be because of the continuity. Okay? And so if the distance here is less than epsilon, that means that f of x sub 1 is an element of V. Okay? That's what we have. Okay? Because this is going to be, this point, f of x sub 1, is going to be in the neighborhood of radius epsilon about f of p. Okay? So if you'd like, we can have just a little bit more details. It's contained in this neighborhood of epsilon by f of p, which of course is contained in p. So that's one way we can think of it. Okay. So that means that f of x sub 1 is an element of v. So that means, that x sub 1 is an element of the inverse image of v. And what was x sub 1? X sub 1 was an arbitrary element of this neighborhood of p. So what we get is that this neighborhood of radius delta of p is going to be a subset of this inverse excuse me, image of v. Okay, let me write that down. So the neighborhood of radius delta of p contained in this inverse image. So that's we've created a neighborhood that's contained in this set where p was just an arbitrary point from this set. So that means that p is an interior point. Of the inverse image of v. So that means the inverse image of v is open. Aha! So that's half of the proof. Now, going in the other direction, we want to suppose that for every open set of y, the inverse image of that set is open in X. Okay? And what we want to show that f is continuous on X. So how are we going to show that f is continuous on X? Well, by the definition, that means that f has to be continuous at every point in X. So we're going to start off by letting p be a point in X, and we want to show f is continuous at p. Okay. So we're going to let an epsilon be greater than 0 be given. We'll use the definition of continuity. And we need a delta bigger than 0, such that for all x, little x here I'll say, in big X with the distance in x between a little x and p, when that's less than delta, that forces the distance in y between f of x and f of p to be less than epsilon. Okay. Well, here's what we'll do. Consider the following set, this neighborhood of radius epsilon about f of p. So that is a set in Y. Okay. So here's what we notice. Every neighborhood is open. Since ends of epsilon of f of p is a neighborhood, we know it's open. Okay, it's open in Y. Now, what are we assuming in this part of the proof? We're assuming that anytime you give me an open set in Y, its inverse image is open in X. So F inverse of this set is open in X. Write that down. It's open in X. Okay, if that's open in X, one thing I can tell you about a set in here, or point in here, note P is an element of this inverse image. Because f of p is in this neighborhood. So p is, with this set being open, an interior point. Of this set. Well, what does it mean to be an interior point of the set? That means that there's some neighborhood of P that is totally contained in this set. So there exists a delta bigger than 0, that's going to be our radius of our neighborhood, such that the neighborhood radius delta about P will be contained in F inverse this neighborhood of f of p. Okay, so here, what we're going to do is we're going to let x sub 1 be an element of this neighborhood about p. Then, to be in this neighborhood means that you're in this set. And so f of x sub 1 is an element of the neighborhood with radius epsilon of f of p. All right. So what are we saying? We're saying for all x in this neighborhood about p, so for all those x's, then f of x sub 1 is in the neighborhood with radius epsilon about f of p. Okay? So what did we just find out? We just found out that there exists a delta greater than 0 the one we produced because P was in an open set. So before I move the camera, what am I going to say? So there exists this delta greater than 0, such that whenever you're a point in here, which means whenever you're a point in big X, such that the distance in big X between P and that point is less than delta, then the distance between, in Y, between F of that point and F of P is going to be less than epsilon. And I'll write that down. Such that for all X, element big X, with the distance in X between X and P being less than delta, then that forces the distance between F of X and F of P, that's in Y, to be less than epsilon. That's what it means for F to be continuous at P. Since P was arbitrary, F is continuous on X. And that's the proof. Now, as a corollary, we can talk about inverse images of closed sets and implying continuity. So let me write that down. Says a mapping F of a metric space X into a metric space Y is continuous. Okay? If and only if the inverse image of C is closed in X, I say. And that's for each closed set C in Y. Okay, we won't prove this. Not sure, even though it's correlated. Oops. So we're going to let X and Y be metric spaces. And map X into Y. Okay, this was an if and only if statement, so we have two directions to do. In this direction, we're going to suppose F is continuous on X. We're going to let C be closed in Y, and we want to show that the inverse of C is closed in X. So here's the first thing. We're going to really use the complements here. So since C is closed in Y, okay, so since C is closed in Y, what that's going to mean is that C complement is open in Y. Okay, what does that mean? Well, since F is continuous, by the previous theorem, and that's why this is corollary to it. F, the preimage, or F inverse, of C complement is open in X. Well, that's great. But what we were trying to show is that the inverse image of C is closed in X. Well, maybe there's a relationship between the inverse image of C complement and the complement of the inverse image of C. And in fact, there is. So here's our claim. Claim is F inverse of C complement is equal, it's the same thing, as F inverse of C, you take the complement of that. So we'll work on proving that. Okay, so how do we prove this? Well, we need to show that these sets are subsets of each other. So let's let X be an element, maybe X of 1 be an element, of the inverse image of C complement. Okay, so what can I say about that? Well, that means that F of X of 1 is an element of C complement. So that means that F of X of 1 is not an element of C. So that means that X of 1 cannot be an element of the inverse image of C. So that means that X is an element of the inverse image of C's complement as, that's what it means. And so we've got one container. That says that the inverse image of C complement is contained in the inverse image of C's that complement. Now, let's let X of 2 be an element of the inverse image of C, take the complement back. Okay. So what that means is that F of X of 2 is not an element of the inverse, I'm sorry, it's not an element of C. Okay? So if it were an element of C, then X of 2 would be an element of the inverse image of C. It's not. It's in the top. So F of X of 2, where does it live? If it's not in C, it's got to be an element of C complement. Okay? So, what does that mean? That means that x sub 2 is an element of F inverse of C complement. And so we just got what we wanted. That is that F inverse of C complement is contained in F inverse of C complement in this fashion. So these two sets are the same. And that ends the proof of the claim. Okay, so what do we know? What we know is since we've shown that F inverse of C complement is open in X, then that means F inverse of C, its complement, which is the same as this guy, is open in X. Well, if that set is open in X, its complement is closed in X. And its complement is F inverse of C is closed in X. And that's what we wanted to show, okay, for that direction of the proof. So we got one more direction to go. Not so much more. This direction, we suppose for every closed subset in Y, the inverse image of that set under F is closed in X. Okay? We want to show that F is continuous. On X. Okay, and we're going to do that from the previous theorem. Okay, so here's what I'm going to do. We let C be open in Y. Now, by the previous theorem, what we'd like to show is that F inverse of C is open in X. And if I can do that for any arbitrary C, then what we've shown is that the inverse image of any open set in Y is open in X, and that's sufficient enough by the previous theorem to show that F is continuous on X. So if this is C is open in Y, then C complement is closed in Y. So by hypothesis, F inverse, the inverse image of C complement is closed in X. So by our claim that we had earlier in this proof, that says that the inverse image of C, that closure, these two sets are the same. Not closure, complement, is closed in X. Okay. That's because of that claim we had in the previous part of the proof. Okay, so we're almost done. So if that set was closed, then its complement, which is just the inverse image of C, is open in X. And that's what we need to show. So by the previous theorem, okay, since the inverse image of open sets in Y are open in X, that means that F is continuous in X. Okay, ladies and gentlemen, that is enough for this video lecture. Thank you very much for your time and patience.